So to remind you, we're continuing with sort of some basic aspects of visual processing in cortical areas, and the focus today is on area MT. I described to you in a few words what is required to generate a sort of the basic elements of for generating a motion selective neuron, and how one can build a motion selective neuron de novo from information arriving from earlier areas. Just to sort of break, this isn't working. Just to remind you, we were talking about this sort of Reichardt detector just in very, very general terms. And then I finished my talk last time speaking about the aperture problem. Okay, now the aperture problem is an example that was dealt with also in terms of physiology. I won't have time to get into it, but I just wanted to mention this. That remember, the aperture problem was the issue that if you have a small receptor field and you have sort of a grid translating in one direction here, in this direction, all you can tell is actually the vector in the normal to the orientation of the lines here, of the grid lines here. Okay, so you cannot differentiate between this direction and that direction. And in order to solve the aperture problem, you need extra information, and that could be accessed from another neuron which is sensitive to a different sort of angle or an edge in the image. Of course, you have to realize there's some tricks here, because you have to really to understand that this is the same object here, right? So the motion of this element here is related to the motion of that element here. Another aspect which is interesting here is that if you record from, remember that I said that neurons in V1, some neurons in V1 are motion selective, and the next area, which is 80 to 90% of the neurons are motion selective, is MT. Well, in MT, you can find some cells who are called Plague cells. If you use such a stimulus, you find that some cells are simply sensitive to the direction of motion normal to the orientation, while other neurons, which we call pattern cells, are already able to integrate information and actually extract the true direction of motion of the object. I'm not getting into this because of lack of time, but I'm just mentioning this because the general theme I'm trying to develop is, and that relates also to what I was talking to when I was talking about primary visual cortex, and if you remember all the psychophysics I brought you last time, suggesting that there's some kind of a Fourier decomposition being made in primary visual cortex by neurons that are sensitive. They have a specific bandwidth in orientation, in the orientation and spatial frequency domain, so that in general the population performs a sort of a 2D Fourier transform of the image, right? We mentioned that. And the question was, can we relate some psychophysical data, such as from adaptation studies, to the properties of single neurons there? And if you remember, I don't have this here, but if you remember, the last thing that I mentioned was, okay, if you adapt to a grading of a given spatial frequency, you get a shift. Say you adapt to a low spatial frequency, you get a shift of the percept when you present a grading to higher spatial frequency, and if you adapt to high spatial frequency, you get a shift to low spatial frequency. And we said something very qualitative about it, not quantitative, in the sense that if you were to use a sort of population vector, sort of, or some averaging mechanism of this distribution, you may actually relate neuronal responses to the percept. Okay, so I'm continuing along this line, trying to relate neuronal responses to a percept, and I think the best example to this is from studies that have been done in MT, this motion selective area, by Tony Knopfchen and Bill Newsom and their colleagues. And what they were using was what we call random dot stimuli. So you had just sort of random dots, either uncorrelated dots moving in random directions, or you could actually have the other case where all dots are moving in a fully correlated way. So this we call 100% coherence dot, and this is a random, completely random motion. And of course, you can have anything in between the two, okay? So here's an example where 50% of the dots move coherently while the others move at random, so we call this a 50% coherence level, or 50% correlation, okay? And I have some videos of the dots just to make the point that it's not dark dots and white dots, they're all white dots. It's just here to explain the fact that the dark dots have the same vector, in this case going upwards, okay? So here's the stimuli that they've used, and of course what's nice about this stimulus is that you can vary the strength of your motion signal in a parametric way, right? So from 0 correlation to 100% correlation, okay? And now, so the idea here was to try to understand perception in terms of the monkey's perception from single neuron properties, okay? And the classic, okay, so how do you go about doing this? Okay, the first thing to do is, okay, have a task that allows you to look at the monkey's performance as well as the cell's performance at the same time. So of course you have to do this in a behaving monkeys. So the task is the following. You have a fixation point. You first of all have to assess where the receptor field of the neuron is. Okay, so you find where the receptor field is, and you place the stimulus at the receptor field, and of course you test what is the preferred direction of that cell. Is that this way or that way? And the way you do this, you present dots in the receptor field in different directions, and you assess that the preferred direction of the cells having the highest response is upwards in this case, and of course the opposite direction is the null direction. Okay? So, and then of course it's important that you will, while you present the stimulus, the monkey will maintain fixation in the fixation point. Why is that the case?
Receptor field is
right. So that's a tricky issue, okay? Because your natural thing is something is shown here, and you have to assess what is it. It's going up or down. Well, the first thing you do is, of course, you foveate it because you have higher resolution in your fovea and greater sensitivity there. So that's a little tricky to keep the monkey fixating in one place and present the stimulus in another, and you have to maintain sort of you have to monitor eye movements to show this, but with training this is possible to establish. So of course, if that were not the case, then the monkey would automatically fixate here, and of course then the receptor field would be here of that cell, and the cell would stop firing. So if we want to assess cell sort of sensitivity compared to the monkey sensitivity, we have to give the optimal conditions for the cell. Okay? So, and then what the researchers did was, okay, the following, they have a fixation point turning on here, and then the stimulus, after the monkey establishes fixation here, the stimulus comes on here, okay? And then the stimulus, while the stimulus is on here, remember the monkey has to fixate, maintain fixation there, and then the stimulus is shut off together with the fixation point, and the monkey reports what was the direction of motion, was it upwards or downwards, using a saccade. So that's another tricky thing. You can't tell the monkey just telling you, okay, if it's upwards, you know, move your eyes here. The monkey has to learn this in some way. That's tricky, but you can teach the monkeys to do this, and then so if the monkey senses motion going upward, it makes a saccade here. If it senses it going downward, it makes a saccade here. So after some time they learn this, and they make the saccade, and you can reward them according to the correct response. So what's nice about it now? Okay, you can first assess the monkey's sensitivity. Okay, so here's the way you do this. You basically generate what's called a psychometric function. So the y-axis here is the proportion of correct responses, and the x-axis is the correlation, percent correlation, or coherence, meaning how many of the dots are moving consistently. Okay, so the 100% coherence performance is, 100%. And as you're moving, this is log scale, but as you're moving to 1% coherence, the monkey's at complete chance, so it's close to here. And of course, as the case in, it's always the case, you have some sort of a psychometric curve, which is a sort of a sigmoid here, and you can sort of fit it with a sigmoid function and extract a threshold, which is at 82% correct. Never mind why, it's not that important here. And you get a value here. Okay, so in this case, the threshold is 6% correlation. So meaning at 6% correlation, the monkey had performed the task at 82%. Okay, great. Now,
just a second. What do you consider correct? If you look, I mean,
what is that?
what do you consider correct?
Correct is that the monkey, remember, so the monkey has these motions, is upward or downwards, and he has to tell which way it is. Okay, so 50% correlation, he's perfect. As you go into lower and lower correlation, the stimulus, there's less information in the stimulus, so it becomes more difficult. So correct, meaning the correct decision. If the dots moved upwards, the monkey said upwards. If the dot moves downwards, he said downwards.
Okay, but
if it's completely random?
Yeah, then what
Okay. So if it's good point. If it's completely random, of course, the monkey can't do better than 50%. Okay, so you don't expect if you found that no correlation, the monkey's performance was above 50%. You're saying, maybe there's something else. There's another cue here that's relevant for the monkey's behavior. But that's not the case. Okay.
But I mean, without thinking about the monkey, is there something that you can consider correct?
Yes, of course. At the 50% level, no. At the 50% level, of course, there's no information whatsoever in the stimulus. So the way you maintain, it's a good point about the monkey's performance. The monkey should still be motivated to perform the task in this case. So you just randomly give him juice every at 50% of the trials. Okay, so that's. How is the threshold computed? So I said the threshold was at 82%. One can show that you fit it with a psychometric curve called quick function. It's not really crucial here, but it's sort of a sigmoid function in which has two parameters. Okay, just to give you a flavor of this, you can fit this with sort of a integral of the Gaussian. And an integral of the Gaussian has two parameters. It's mean and it's standard deviation. Something very similar to that. Okay? Basically, that's the idea. Now, going back to the neurons, okay, we're talking about the neurons. Well, the other question is, how sensitive are the neurons to the stimuli? So the way to assess this is basically to use, look at the variation of the response for a repetition of the same stimulus. So for those, so I'm sure you've heard something about this already, that the neuron itself is not responsive exactly the same if you present the same stimulus. Why is that? Many reasons. Could be noise or could be signal. The monkey is less motivated to do the task, and unclear. But in any case, what you can see is that when you present the same stimulus. So let's look here. Okay, so you have a distribution here, the Y distribution here, which describes the firing rate of that specific neuron when the stimulus was at 12.8% coherence. So this is when it moved in the preferred direction, and that's when it moved to the null direction. So notice here that if you look at this Y distribution here, it's not exactly the same. So sometimes the neuron fired, 75 spikes per second, but sometimes it fired less than 50 spikes per second, right? And if you look at that's the null direction, well, on average it fired less than 50 spikes, but sometimes it fired above 50 spikes, okay? So that's sort of a distribution of the response for the null direction and for the preferred direction. Now, if you reduce the coherence, I got the wrong batteries. Okay, so if you go and reduce the coherence, notice what's happening. What's happening is that this distribution of response to the preferred direction, null direction, their overlap increases, right? So the way to tell, now think about it this way. First of all, intuitively, you are sitting in the other room, listening just to the output of this neuron. Can you tell if it's in the preferred direction or in the null direction? Well, if you're talking at a high coherence level, it's relatively simple, right? Because there's sort of a criterion you can use to say, okay, above it is the preferred direction, below this is the null direction. But as we reduce the coherence level to lower and lower levels, I mean, think about here, these two distributions completely overlap, right? So the information that you have about whether it's in the preferred or the null direction is largely reduced to null. Now, one can assess this using what's called signal detection theory. So here again are these distributions, and the way to think about it is the following. Have you heard anything about signal detection theory? Have you heard anything about this? No? Okay. So signal detection theory sort of is a technique developed by psychophysicists and applied here to the single cell data in order to tell something about the sensitivity of your detector. Okay, so the classical way to think about it is, okay, it was developed in the 40s by the British, and the idea is, or think about that the classical situation in which you're in front of a radar screen and you hear a blip on the radar screen. Is this the Luftwaffe coming to bomb London, or is this just a noise in terms of a flock of birds? Okay, and of course, one can think about it. The blip on your radar screen is going to vary from trial to trial, based on your attention, or there could be noise in the actual sensing mechanism, and also internal noise in terms of your sort of alertness or something like that. So you see now I hope you see the analogy to what we're presenting here. So the way one can assess this is to do the following. You're basically, let's say you take this distribution and you're changing your criteria. You're saying, okay, I will apply, maybe I'll do this here. I'll apply a criterion to say, okay, when do I alert the RAF to go and to intercept the planes? And of course, one can think about this as the following. So the x-axis here would be the blip magnitude on your signal, and the y-axis would be the frequency, the chance that you're going to get that sort of magnitude. And you have a distribution here for your signal. So this is the signal, okay? And generally, the signal is greater than the noise. That's for the noise. But one has to decide on a criterion, okay? And you say to yourself, okay, I'll set a criterion which would be here, okay? Anything below this is more likely to be the flock of birds, and anything above this is something that, okay, needs to draw my attention and to call the pilots to jump to their planes. Okay, now of course, notice here, there's a few things to notice here. What would be the optimal policy?
Depending on your cost function.
Exactly, depending on your cost function. And for those of you who do not come from this, what do I mean by a cost function? There's a cost to calling the RAF pilots while it ends up to be a flock of birds. But they lose their sleep, they're getting angry at you. You don't want to do this too often, okay? On the other hand, there's maybe a greater cost, okay, in the case that you do not call them and it ends up to be the Luftwaffe, right? So you want to sort of set your criterion. So this is the criterion here, okay? And you want to set your criterion according to the cost function, meaning, okay, what is the cost for one action versus the cost of another, or one, I wouldn't call this an action, I would call this a result versus the cost of a different result, okay? Now, so the way to think about it is, let's divide this distribution into different outcomes, okay? And so let's think about it. What would we call a hit? A hit is when we called the RF, and there was good reason to do this. And what is that? That would be this up to the criterion here. So the area under so think about this as a Gaussian distribution. The area under the Gaussian from minus infinity to plus infinity is 1. And of course, if you take this is less than 1, okay? And you can, and the area here compared to the complete area is the probability of that outcome. Okay, what is the outcome that we called the IRF, and in the end it happened to be a false alarm? Okay, so that is this one. Okay, this should go down to drop to 0, of course. And what is that? That is this. Right? Okay, so this we call a hit, and this we call a false alarm. All right? And of course, the complementary ones, okay, anything below this, I think you can follow that the complementary ones are just one minus the false alarm would be the correct rejections, and one minus the hit would be misses, right? So we want to minimize, okay, when we were talking about the cost function, the misses are, I'll draw this with another color. There is one. That would be, of course, the miss. And, okay, bad outcomes, of course, are false alarms and misses, okay? And depending on the weight we give to them, we're going to set up the criteria. If the miss and the false alarm we give them the same weight, then what would be the optimal criteria? Right here, right? Right, because then if this is the criteria, then the areas of the two are the same. Okay, anyway, that's the basics of it, okay? That's just the essentials of it, of signal detection theory. And so what you can do, interestingly enough, let's say that you have two distributions. You can compute let's make another one point, and that is the discriminability between the two distributions. So what is the discriminability between the two signals? It has to do with two factors here. One is the mean here, and the distance between them, right? So the further they are, the more discriminable they are. And the other is what? The standard deviation, right? The standard deviation, exactly. So D prime, the discriminability is mu sigma minus mu noise divided by sigma, assuming that in this case that standard deviation is the same for the two. Okay? And so there's two parameters that one can extract, D prime and the criterion. Okay. And let's look at it here. Okay, so what are we plotting here? Okay, so we want to take this and extract from this the sensitivity of the neuron. Remember, going back to what our task was. How are we going to do this? We're going to plot here the y-axis is the probability that the preferred is greater than the criteria. Okay, and here it's that the null is greater than the criteria. So this is corresponding to the hit rate, and this is corresponding to the false alarm rate. If the null is greater than criteria, what does it mean? That null is the noise here, that the noise is greater than the criteria. So that falls under the false alarm rate. Okay? So this is false alarm rate against hit rate. Okay? Now, and this is called the receiver operating curve, ROC curve. Okay? Now let's try to analyze this. Okay, if the two distributions, just to see if you understand, if the two distributions are completely overlapping, what would be the result? Okay, right, something along here. Think about them. The two distributions are completely overlapping. So as I'm changing the criteria from minus infinity to plus infinity, I'm increasing both the hit rate and the false alarm rate at exactly the same way. Okay, and if the two distributions are completely non-overlapping, zero overlap, what would be the result? You've heard this before? Okay, well, so I'm happy to. Okay, so it would be something along here, right? I mean, you immediately go to 100% hits without incurring any false alarms. Yes.
Can you repeat what each axis means?
Yes. Okay, so the x-axis is the percentage of the null being higher than the criteria, meaning that the noise, null we call noise here because it's in the wrong direction, being bigger than the criteria, and you can translate this to the proportion of false alarms. And here, this is the preferred being the criteria. That would be the proportion of hits. Okay, so the proportion is always between 0 and 1, right? Okay, and so it's bounded by 0 and 1. And as I said, the main diagonal, and what we're doing is changing the criteria. So I'm not sure if I made it clear. The criteria, I set the criteria here. What is the rate of the hits here? Give me an answer. Okay, so here's the preferred direction, here's the null direction. I'm starting from here, and I'm moving the criteria this way. How many hits am I going to have here? 0, because none of the cases we had the firing rate, above that level. As I'm moving here, okay, now suddenly I'm getting a hit, right? No false alarm. So as I'm increasing here the criteria, what am I doing? I'm moving along this dimension here, right? I'm increasing the rate of the hits, okay, without incurring any false alarms. When do I start incurring false alarms? As I get to here, right? So as I get to here, there's the first false alarm. Is this a perfect, what would be okay, now that you've seen this, what would be the performance here? Would it be completely perfect? No, because there's some overlap between these two distributions. Okay, I think we talked about, so, and then that's basically the way to sort of assess this. And so the end result of this is that if we've shown the psychophysics, you can do the same with a specific neuron, okay? And get an idea of what is the sensitivity of a specific neuron, okay? That is the beauty of it, okay? And now, I won't take too much time here, but the idea was that, okay, if you do this, you see that some neurons are more selective to the direction of motion in terms of needing a lower signal in order to discriminate between the preferred and null direction than actually the monkey is. While others, okay, so here's a case where, okay, so the two psychometric and neurometric curve, if they're completely overlapping, means that the thresholds are the same. If this is the case, well, one is better than the other, right? The further you are to the left, the better performance is. Is that clear to everyone? Okay? So here's one cell, here's another. I don't remember which one is the neuron and which one is the monkey, but you can tell that, okay, in one case, let's say that the neuron is in the white circles here, so the neuron is more sensitive than the monkey. And here, the monkey is more sensitive than the neuron, okay? And in some cases, they're the same. Sometimes it's better. And in general, what we find is that the sensitivity of the neurons, on average, okay, the average neuron here, so is just as good or almost as good as the monkey. So how do you do this? You can do the threshold ratio, okay? So let me make this clear again. So here you can extract the threshold, right? So the threshold of the monkey and the neuron are just about the same here, almost the same here. One is bigger than the other here, and the other is bigger than the one here, right? And you can now do this across, 200 or so measurements that they've done, and basically they get that the threshold ratio of the neuron is as good as behavioral. A little slightly worse because it's somewhat bigger than one here. The distribution, it's a normal distribution log plot, but it's somewhat shifted to 1. Okay, so it's 1.19. Okay? Is that something that you find surprising? Not surprising? Okay. So some of you have heard me in my course that I give to undergrads, so might have heard this. They have heard it. I don't know if they remember anything about this, but is it surprising or not? A bit surprising, and I would say quite a bit surprising. Why?
Single neurons.
Single neurons and behavior. I mean, okay, so assuming that you are to, I don't know, you move your electrode and you kill the neuron. That happens sometimes, okay? The monkey's performance doesn't change, okay? So, and evidently, the monkey doesn't use single neurons to come to a decision. And I would say the following. Yeah, just 1 minute. Okay, you want to say something?
But this is our large number of cells. This is not one neuron.
No, but each experiment, you're optimizing things for one specific neuron and measuring the neuron sensitivity and the monkey sensitivity. The next day you come and you do this with another monkey, another neuron. So
It's not 1.19 for one neuron.
for the average neuron, okay, exactly, the average neuron. So yes, indeed,
That's why
some neurons are much, much better than the monkey. Okay, it's not, okay, if you say, okay, well,
on average it's the same thing. So when you kill one neuron, then of course the
okay, so you say, okay, there's many other neurons which have similar performance. And I would say there's actually some neurons which are 10 times as better, okay, the ones here, 10 times as better as a monkey. Well, if you're to use single neurons, why not use the best ones? Right? So it doesn't seem reasonable to think that you're actually using single neurons from a number of perspectives. So how can you understand this? I'll jump to this. This is just to show that, maybe I'll mention this, just to show that the neuronal threshold and the psychophysical threshold, these are different measurements. Each point here is one neuron studied in one day, right? So the neuronal threshold and psychophysical threshold are generally uncorrelated. That's very important. Why? Okay, because if it were, I would think that, okay, maybe the monkey, and remember, you're recording the output of that specific neuron. And you hear the output, let's say, in the audio monitor here. Okay? Well, maybe the monkey hears the same audio output, and he uses the output that you actually have to guide his decisions. Now, we don't want that to happen, right? We want this to be based on the firing of a neuron, but not through our devices, auditory devices, listening to that neuron, okay? And in that case, you would think, oh, well, maybe it would be correlated. Okay, but on the average, it isn't correlated. Again, pointing that it's unlikely that it's that specific neuron that guides behavior. And as you said correctly, of course, if you kill the neuron, nothing happens to behavior. So how can one understand this? Okay, how can one, let's think together, okay? So there's this sort of an enigma here of you have that the monkey's performance is much worse than one would have expected if you were to pool the information of many, many neurons. Okay? Now, let's think about it this way. The point in terms of signal detection, the way you should think about this, but the way you could think about this is that you have, say neurons which, if you are presenting a stimulus, there's sort of a distribution, that's the firing rate as a function of the, say, the motion signal. Firing rate. This is frequency here. Meaning how many times you fired at a given rate for a specific stimulus, okay? So this would be here, firing rate. Just as we saw before, okay? So for a given stimulus, that specific neuron fires, let's say, 50 spikes per second, but there's some distribution of responses that, due to noise, so that it doesn't fire exactly the same when you present the same stimulus. That's what we've seen before, right? You're with me? Okay. Now, if you were to pull many, many neurons, let's say that they're exactly the same as this one. What is the expectation?
Sorry.
It's called average. Yeah.
Can you please explain again what you mean?
Yes. Okay. I'm sorry. Yeah. I know. My fault. Let's go back to here. And we said, okay, what is the inherent problem of the single neuron? The inherent problem of the single neuron is that there's some noise that we cannot control, okay? Meaning that you present, that's exactly what I showed there, you present the same stimulus over and over again, and the firing is not exactly the same, okay? So there's some inherent noise. And I'm saying, okay, how can we deal with this? And of course, that noise limits your performance, okay? Because the sigma here limits your performance here. Okay, now we want to basically reduce that noise. So how can we do this? Well, one way to do this is through averaging. Okay, let's think that you have exactly the same neurons, many replications of the same neuron. Okay? If you're going to now have basically summation of such neurons, okay? Each of them is the one, replicas of the one that I've described, then what you expect, and now you look at that mean firing rate of the summator, then it should be something that looks like that, right? Because you're basically now doing just an averaging, and now you get rid of the noise by the fact that you're summing many, many of these inputs, okay? Now that's true.
I think the two bars should be reversed, right?
Yeah.
The two bars should be reversed. This is fine. This is
What should be reversed?
the
Axis.
yeah.
That's frequency, meaning that the chances that you...
It should be fine.
Frequency.
No, it is frequency.
How many tries it has?
Yes, exactly. When I'm saying frequency, it's in how many cases did it fire X spikes. It's exactly what we see here, okay? In some cases it fired X spikes, some cases it fired more. So it's exactly the same as here, okay? So that's frequency. The chances of firing, I don't know, X spikes, okay? So it's not, and indeed, so the axes are right.
I don't see why you call, I mean,
So I'm saying is if you were to look at now the variation of this summator here, assuming that the summator just sums this input and calculates the average, okay? It calculates the average, okay? So if you're taking, and this is mu1, and you're just doing the average of sigma mu1, okay, mu I, okay, from 1 to, I don't know, 100 such neurons you're summing up, and you're trying to compute the average of this one. So the average of that would be the same as the original neuron, okay? But its standard deviation, okay? The noise would be much smaller, okay? And the noise would be what? Let's just get to what would be the standard deviation of the noise? So sigma of the summator would be sigma of mu divided by square root of n, right? I mean, and that is in what case is that?
They're independent.
Only if they are independent, right? So I'm saying, okay, why not use the summator, okay? Use a summation of pool the information from all these neurons to get a sort of an average signal, and then you'd expect maybe that your performance is going to be much better. It's going to be this 1 over the square root of n. But you do not see this. Okay? And so...
Can I ask
Yes.
a more basic question?
Basic is fine.
Understand the graph itself, not the thing with the summation, but before that.
The graph itself plots the firing rate, the frequency of getting a specific firing rate, just like we've had here. So you're presenting, say, a stimulus at, I don't know, 12.8% coherence, okay? And you're presenting it over and over again.
Like
You-
the histogram?
Yeah, it is yeah. It's just like here, but now I just sort of did this in a sort of ideal way where it's sort of a Gaussian, okay? If you were to do this many, many times, you'd see a Gaussian, okay? So this is the firing rate in the x-axis as a function, and the y-axis is the chances of getting a specific firing rate, okay? So okay, and this is for the individual neuron, and here we plotted the average firing rate, if you were to pool many, many neurons like this, of the summator, okay? Okay, so that is the issue here, and the one thing that we I want to lead you to think is, okay, one way to understand this mismatch, in the sense that, okay, you would think that we are able to pull information from many neurons together, is the fact that they may be correlated. Okay, so, okay. Another thing that I want to sort of draw your attention to is another sort of behavior. Remember that the monkey is given stimuli of different coherence levels, okay? And sometimes he's given stimuli which are completely random, right? We call them zero coherence level. Okay? Now, what we can do, of course, in that case, the motion is completely random, but we can sort the data according to the monkey's decision. Okay, so he sees random motion, but this one's upwards. He sees the same random motion, and another trial says, this one's upwards again, but the third time he says it's downward, right? So what we do here is plot, so this is a number of trials, okay, so there were, 60 repetitions of the same stimulus over and over ago, and here we record the firing rate of that given cell when the monkey reported that it was in the preferred direction, and when he reported it was in the null direction. So the preferred direction is open circles, null direction is darker circles. Very, very surprising here, right? Why? Because what do we see? If we sort of pool them, we see that, okay, this is the distribution for the preferred direction, and this is the distribution for the null direction. You'll see that the distribution, when the monkey reports that the motion was in the preferred direction, firing rate is higher than when it reports that it was in the null direction. Remember, physically, the stimulus was exactly the same. It's just the reports of the monkey. Okay, so what you get here is a difference due to what the monkey reports, not due to what was up there on the screen. That's exactly the same. Okay? So it suggests that the fluctuations, 1 minute here, the fluctuations in the monkey's response from trial to trial are somewhat related to the fluctuations in the cell's response from trial to trial. I mean, that's what we see here. And so that it suggests that the cell has an important contribution to the monkey's decision, right? If it were not the case, you would not expect this, okay? Now, of course, I see some disagreement in the background. One has to say that this is just correlation, okay? It's not causality. And we'll talk about causality in a minute here. But this is sort of suggestive that cells have significant contributions to the monkey's decision. Again, yeah, again, 1 neuron. Okay, just as we said before that the 1 neuron's sensitivity on average is as good as the monkey, the 1 neuron's fluctuation from trial to trial can explain somewhat. Okay, it's not a full explanation here, of course, because these two distributions are largely overlapping. But there's still a higher firing rate on average when the monkey says preferred direction than when the monkey says null direction, although there's nothing on the screen. Again, it sounds weird because if you're using many, many neurons, okay, you don't expect that the fluctuations of a single neuron are going to affect behavior. Okay, so that is sort of putting this down. And just 2 more slides before we take a break. Okay, so how can we understand this? Okay, so the first thing is what I said is, okay, one can think about this. You have sort of a population of cells selected to the upwards motion and another population of cells selected to the downwards motion. Okay, and how do you arrive at a decision? It's very simple. You just compare the output of something that sums up the information from the upward cell, another neuron that sums up the information from the downward cell, and you just compare them. If this one is bigger than that, then upward. If this one's bigger than that, then downward, right? So it's sort of a toy model to think about this in terms of sort of pool information from many, many neurons. Okay. And we said that if that were the case, if you were to pool many, many neurons, if they were independent, you're going to get much, much better. You're going to get, the standard deviation is going to drop as a function of the square root of n, and therefore you expect that performance is going to get better as a function of the square root of n. But we don't see this. So how do we understand this? The way we can understand this is to think about the neurons as being somewhat correlated. Okay, that the noise of one neuron is correlated with the noise signal of the other neuron. What do I mean by that? So say that you present a given stimulus, motion 12.8% coherence upwards. Okay, here's the firing rate of neuron 1. Notice that you give the same stimulus, there's some variation in the response of neuron 1. Okay, and here's the response you record from the same, in the same case, from neuron 2 as well as from neuron 1, and you get some variation of responses in neuron 2. But the question we're asking, are they correlated? If they're independent, they should be uncorrelated. If they are correlated, then it should limit your ability to gain further information by pooling signals from more and more neurons. Okay?
Why is it not the case that the performance gets better as functional?
Again?
Why do you say that it's not correct that the performance is better as a function of n?
Okay, so
How do you know?
okay, we don't know, in terms of the performance as a function of, we don't know what n is, right? We have no idea how many neurons are being used by the monkey to arrive at a decision, okay? But as I'll show you, okay, as we showed, let me explain the graph here. I think that will be an answer to your question. If I'm not, please stop me, okay? So what you show here is on the x-axis the number of neurons used in the pool, okay? So the greater number of neurons, you'd expect better performance, right? And the y-axis here is the signal-to-noise ratio, and that is basically just the sort of a ratio of the standard deviation of the pooled signal, which is just sort of a function of 1 over square root of n if they were independent. So that's what you see here. So if you look at the signal-to-noise ratio for independent cases, shown by r equals 0 here, you see that there's following a straight line, okay? This is the log axis here, okay? So if you are to, instead of using 1 neuron, use 100 neurons, then you expect the signal-to-noise ratio to improve by what? Square root of n, and therefore it goes from 1 to 10, okay? If you were to use 10,000, it should go up to 100 here, right? But this is just an analytical result. We can, I don't have time to get into the full details of this. What happens if you have very, very slight correlation between the neurons? Okay, so as we see here, it's not completely uncorrelated. For completely uncorrelated would be a sort of a Gaussian, 2D Gaussian sort of cloud here with no correlation between the 2 points here. And you see that there's some slight positive correlation between the 2 points here. Now, one can show that, and that is somewhat surprising, that even if the correlation coefficient between the 2 neurons is very, very small, okay, it's of the order of 0.1, okay, meaning that when one neuron fires above its mean, the chances are that you're going to see also that neuron 2 fires above its mean here, okay? So it basically measures the covariance between the two, the degree of covariation of firing between the 2 neurons here. So even if you have a very, very low correlation, I mean, correlation of 0.1 is something that's undetectable. You would not be able to see it, basically. But you can compute it, of course. Okay? You can see that it limits the increased amount of signal-to-noise ratio that you can get from pooling more and more neurons. It basically reaches an asymptote here. So we don't know, to your point, we don't know if you're using 100 neurons, 10,000 neurons, or 10 million, or 10 billion neurons, okay? But all we can say here is that given the limited correlation that we find between the neurons, you already reach sort of an asymptotic performance, so that your performance is going to be maybe twice or 3 times as better as a single neuron, but not, if you were to use 10 billion, you'd expect that, okay, that performance should be, 100,000 better, or square root of 10 billion, okay? So it's much less than you'd expect if from the case in which the neurons were independent of one another in terms of their noise. Okay, now why is that? Why are...
Assume that they're not independent.
It's not assuming that they're not independent. Okay, I forgot to mention, this is a measurement that you do. Now we measure the degree of correlation between individual neurons. How do you do this? You just record from the neuron, one neuron, another neuron that you record simultaneously, and now you present the same stimulus. And you look at the degree to which the variation of neuron 1 is correlated with the variation of firing in neuron 2. Okay? And you get something, a cloud like that. You can fit it with a sort of linear, with a line, and compute the correlation coefficient. right? Correlation coefficient on average is usually of the order of 0.1 or something like that. Very, very weak correlation. But the point is that even in such a weak correlation, you get very little improvement of the signal to noise as you're increasing the number of neurons that are playing in your decision process. That's to say, yes, just one last thing. That is to say that, okay, we don't know. Again, we don't know if you're using 100 neurons or 10 million neurons. But all we're saying is, given that the correlation measured between the neurons, you do not expect them to, the monkey's performance to be, orders of magnitude better than the neurons. So that's sort of one explanation to the phenomena that we see. I'll 1 minute here because I want to finish and then we take a break, okay? So I realize that we're running late here. The other point I want to mention here is the second phenomena that I mentioned, right? That then you looked at the zero coherence level where the motion was completely random. You saw that you could predict from the cell's response what will the monkey report. Is it in the preferred direction or another direction? Although there's no signal. Okay, how do we understand that? Well, you can show again that the correlation between a neuron and a pool. So we're assuming that the decision is based on, you compute a pool signal here and a pool signal here and you compare the two. Okay? So the question is, okay, if the neurons are correlated with one another, let's think about this intuitively. We expect that the higher they're correlated, the stronger the correlation will be between the neuron, the individual neuron, and the pool. So think about it this way. Okay, if they're completely correlated, if they're completely correlated, okay? So I'm listening to neuron number 1, and it's a bit noisy, so it's responding somewhat different from one trial to another. And now I'm taking number 2 or number 3 and number n, and I'm completely correlated. I don't gain anything from listening to the n neuron instead of the 1 because they're completely correlated on trial-by-trial basis. Okay? Now, if they're completely uncorrelated, of course, you're gaining more and more by adding more and more neurons. And one can show that if the correlation coefficient between the individual neurons is very weak, it's of the order of 0.1 or something like that, you see that there's still remaining a correlation between the neuron and the pool, the neuronal pool that I said here, although each neuron is correlated with every other neuron very weakly. Okay? And so again, this can one can show this analytically that this is indeed the case. And then again, it sort of makes the point that, okay, we've seen something which looked really ridiculous, the fact that the individual neuron fluctuations are correlated with monkey decisions here. So that's a way to understand this. Okay, I took your time 7 minutes, so we'll take a break here. I'll take questions on this as we come back and we'll continue.
Two announcements. First thing, hopefully you're here, or the vast majority, and that's good. If someone can't come to the class, just send me an email, no problem. And the second thing about this, the class, well, this is really, I'm not sure you understand, this is really fundamental, and this is really excellent work of Udi and...
No, it's Bill Newton. I was supposed to... So really,
I think, there's a paper that Udi is presenting, is a paper from '94, really opened the whole field in neuroscience, cited thousands of times, and just appreciate it.
כן, אז זה קורלציה בין כל זוג נושא. היא מאוד מאוד קטנה. האמת שזה למה זה נראה ככה? זה לא רק למה זה נראה ככה? כל אחד מדבר בקורלציה נמוכה עם באיזשהו שלב, אתה הולך אותה. אוקיי, אבל קורלציה נמוכה, למה כשאתה מוסיף עוד ועוד ועוד, אין לו עוד ועוד תוספות. עוד ועוד תוספות לעניין הזה, שתוכל להרוויח משהו מהסיגנל. אבל הבעיה היא שכל אחד, עכשיו יש לך, כאילו אינטואיטיבית, כל אחד עם קורלציה עם אחד עם השני שהיא מועטה. אבל יש לך יותר, אז יש יותר צירופים אפשריים. אקזוסטי את האפשרויות בעצם להרוויח משהו מזה כשיש לך המון נוירונים. לכן, כאילו, זה נראה מאוד מאוד, כאילו, אותי זה ידעים, באמת זה ידעים, כאילו, לא היה לי אינטואיציה כזאת. לפני כן, עד וכאילו, מתמטיקה שלנו מאוד פשוטה, זה קצת קל להסביר, הוא מזמן להיכנס לזה. אבל זה באמת מציע, זאת אומרת, בעצם, כאילו, את לא מרוויחה, ולכן, כאילו, השירה שלך, אין לי מושג, אף אחד לא יודע להגיד על מה מבוסס הטיפול של הסיגנל הזה. וגם אני חושב שכולם משוכנעים, וזה ברור לגמרי, פה בצורה הזאת נותנים טיפול דק. זה לא שחושבים שיש באמת נוירון אחד שהוא לא מסתכל של כל האינפורמציה ונוירון שני של האינפורמציה של למעלה ואתה משווה את זה. לא, ברור שזה לא ככה מסתכל. אבל אתה כן חושב שככל שיש יותר, אז יש יכולת לשיפור בביצוע. אוקיי, אז...
כאילו על זבון מסוים.
מה? לא, ופה זה מראה שבעצם זה מהר מאוד. כשאף שווה לאפס פה, אז באמת, ככל שאתה הולך ומגדילה את מספר הנוירונים, אז הציפייה היא שהקורלציה בין הנוירון הבודד ובין הקור, היא תלך ותרד לאפס. כי לא סביר שהפלוקטואציות בנוירון הבודד, איך ישפיעו על הקור, רק אם כולם ביחד, מתנגדים ביחד, אז תוכל להבין איך הפלוקטואציה של הנוירון הבודד יכולה להשפיע על ההתנהגות של הקור. כי זה לא משקף את הנוירון הבודד, זה משקף את האופוזיציה. זה האינטואיציה. Yes, yes, sure. I'm listening. I'm just having.
So neuron pool correlation, the pool correlation is the average of all neurons.
Exactly. You take this signal here, the average signal here, and you say how correlated with a specific neuron. Okay. Because you're saying that the pool is directly related to decision. Okay. What we're trying to explain is the fact that I said before is that the individual neuron fluctuations can partially explain the monkey's behavior on trials where there's no information in the signal itself, in terms of the stimulus itself is completely random. Okay, and still, it seems very peculiar that the fluctuations of the individual neuron are going to be linked to the monkey. Well, you know, a monkey is clearly averaging across many neurons, so how can that be? So that's trying to explain that. And again, the figure here is there was no correlation between individual neurons.
Yes.
Okay, in the firing rate of the individual neurons.
I think if you explain this part.
Yeah, so now you understand that.
Yeah, I understand.
So you understand that graph here.
Okay.
Okay? But that is the surprising thing here. I mean, one thing that unless you I didn't have the intuitions.
Simulation, right? This is no real data.
It's not a simulation, it's sort of analytical. It's analytical. Analytical, but it's not data. We don't know how many neurons are used for the pool, you know.
Okay.
So it has to be, of course, but it is something that you can, given basically you can look it up in the paper. I can give you the paper. It's very simple, but it's counterintuitive to the fact that you think, well, wait, if you have more neurons, and the correlation is so weak between them, how is it that you exhaust all the variables? Okay? How is it that you cannot, by using more and more neurons, sort of, I'm meaning that you have an asymptote. Why do you have an asymptote here? Okay? That's somewhat surprising. And the idea is that, okay, the correlation between each two neurons is very low. But think about this, if you have, let's say now, instead of 2 neurons, 3 neurons. Well, you're sort of limiting yourself that each one has to be correlated with the other to some extent, okay? And when you're increasing this, at some point, you cannot gain much because you add n plus 1 neuron and everything is already, so the situation is already frozen by the correlations between these n neurons, the pairs of neurons within the n neurons.
Can I ask one more question?
Yes.
So here is so the average neuron threshold is higher than the behavior.
Meaning that the neuron is the average neuron is slightly worse than the
okay. Yeah.
Slightly worse, but okay, you would expect this maybe to be, I would have, again, slightly worse, but very close to.
So I mean, so that also means that for the pool, it will make a better decision than single neuron. Right?
Yes. But
it's very close.
Yeah, it's very close. Okay, and again, to be completely fair, I mean, if we go here to the model, we still have we solved most of the problem. We haven't solved it completely because the signal to noise here is still sort of, with our 0.1, it's of the order of, 3 times better. So you would expect 3 times better, not 1.2 times better for the behavior to be better than the neuron.
Yeah.
But it's okay. It's 3 times better. It's not that if you were using 10
yeah, but probably they have very high correlation, right?
No. So the correlation is of the order of 0.1.
Oh,
If you measure the correlation is of the order of 0.1.
Oh, okay.
So it's within this area here. Okay. It's
So probably use few neurons. It's maybe just use.
Yeah. So we don't know. We don't know. But okay. But it's clear that you have a problem of explaining something of the order of factor of 2, not a factor of 1,000,000. If you were to use, as I said, if you were to use 10,000 neurons, then the signal to noise should be better than an individual neuron by a factor of 100. Okay. So you've reduced this to something on the same order of magnitude. Okay. That was the point. You follow me?
Yeah.
That was okay. We can live with a difference of factor of 2 like that. We cannot live with a factor of 1,000,000 or something like that. Yeah, and of course I have to stress again that we don't know how many neurons are used in the pool. We have no idea. Okay? Could be 100, could be 10. I would think that many, of the orders of millions, not of the orders of tens or hundreds. Okay, so clearly, this is some way to start understanding this. I mean, we haven't solved it completely, but we have solved it a little bit.
Thank you.
You're welcome.
One question also I have. How is it that one monkey can say, for example, you were saying that they can predict the one neuron's preferably motion, like if the receptive field of a neuron is up, and then the monkey can predict that it's up. When you were saying that.
I'm saying, okay, I was. You mean this graph? Wait. This one?
Yes.
So here you're saying the following. You're saying this is completely random motion, and on trials in which a monkey says that it's upwards, okay, let's say that the spread direction of that specific cell is upwards. So when a monkey says that it's upward, it's on average somewhat higher than when he says that it's downward. So there's no physical difference between the stimuli. It's the monkey's decision, right?
That monkey decision is based on many neurons.
Right, okay, so exactly. So here, you see that if you were to compute how predictive the neuron is of the monkey's decision, it's about, 55%. Not 50%, 55%. Slightly better than the chance. And you see that they are overlapping to a great extent. But it's not 50%. Okay, it's not chance. And you're right. I mean, how is it that if you're using, one neuron, how can it predict the monkey's behavior? So that was the point I was trying to make here, right? Okay, that's okay. If they're correlated, the neurons are correlated. Think about them that they're correlated together. So they're fluctuating from trial to trial. Now, if they're fluctuating from trial to trial, of course, and one neuron is fluctuating just as the other, together, of course, the specific neuron is going to be indicative of the neuronal pool. Okay, now the interesting thing is that even if they're very weakly correlated, it doesn't drop. If they're uncorrelated, you see that it's dropping to 0. The more neurons you're using,
Less correlation.
yes. But we see that this is of the order. When you measure the correlation, you find that it's somewhere around here, okay? 0.1, something like that. It's not 0.5. Correlation between each neuron, okay?
So this means in the last graph you were saying, if you compare each neuron with the animal decision of the receptive field, you will see the same correlation between each neuron. So
yes. I mean that's
like in the last, like
like this.
If I change the neuron, I will see basically.
Yeah, so there's a variation here as well, but it's of the order that most of them. I didn't give you the statistics, but most of them will convey some information. It's better than 50%. Okay, it's better than 50%. There's some variation. Some would be 58%, some would be 53%. But if you look at the distribution, it's better than 50%.
Something that no one expected, I guess.
Exactly. And this interneuron correlation between the neural pairs, that's a way to understand it. That was the point. Okay.
All empty neurons, right? Yes.
Empty neurons.
זה גם הנחה למה הביקורת, איך אני מסתכל על המסגרת. אבל שלא, זה וקטור. זה לא את הקשר בין תפק פעולה כזאת. אני מסתכל בדרך כלל של אוכלוסייה, מה היה? זה נגיד משמעות. המשמעות של זה שבגלל שהמעלה לא בלתי תלוי, זאת אומרת שהאינטרקונקציה, אני מקבל איזשהו קשר שאתה עבודה אצל מקבל גם איזשהו, ויש גם החלק הראשון, זה גם יקפיד כמה אני יכול לקבל. זה מה לא אבל behavior עולה, עולה כבדה, אתה עובד, מה שאתה המסקנה היא שבגלל שאני מתאים למשהו יותר קטנה, לא יכול רק בכלל לזה,
כאילו, לא אני סקשן, אבל זה משהו שאני אמורה לראות
discrimination.
אז לא אמור להיות ה-50% של העקומה פסיכומטרית?
לא, כי פה את עושה... את מתחילה מ-50%. 50% זה 100% זה פרפקט... לא צריכה להגיד אם זה נגיד למעלה או למטה, זה הפרפרד או עלה. 50% זה צ'אנס לגמרי, נכון? אז פה זה הקוהירנט. זה לא משהו שהוא נראה ככה, נכון? ואז אפשר לחלץ את זה, אפשר להסביר למה זה 82%, זה לא משנה, זה די ארביטררי. 50% זה כמובן אין חשוב אינפורמציה.
איך נבחר?
זאת אומרת, מה הקוהירנס לבל הדרוש בשביל שהביצוע יהיה 82%?
למה 82%? לא, כי אני מסתכלת על העקומות הפסיכומטריות, וכתבת למטה מה זה שדבר בסדר, איפה הגיע לי?
אז אמרתי, זה ככה, זה ב-82%. עכשיו, למה? כי את מתאימה פונקציה שהיא נראית T של X שווה, אתה זוכר בעפה?
לא.
זה אקספוננט של... כן, באופן... כן, לא, זה לא, זה הולך, אני בעצם ככה, אם בחזקת מינו, אני צריך לנסות להתאחר. כן, יש כמה דרכים להתייחס לזה, אני חושב כן, עכשיו, אחד למה אני במקום לנסות לנחש כמה לעשות את זה, לשלוף את זה מה אני רוצה להמשיך עכשיו, אז אני מיד אחרי זה, זה נקרא quick function. זה quick function, יש שני פרמטרים, כמו שאמרתי, רק זה logistic regression מה שיותר, זה משהו בחזקה, אוקיי? אז יש משהו שמתאר, אחד שהוא מתאר את זה, אפשר להראות, אני לא זוכר את הבעל פה פשוט, אוקיי? אבל אני בקלות יכול להראות לך, אתה תמשך דקה אחרי זה, ברגע שאני אשמור פה.
אבל זה expression של detection.
כן, לא, אתה צריך discrimination בין למעלה ולמטה, אוקיי? תבוא אליי גם אחרי זה. זה בטח. Okay, so I hope I've answered your questions. If not, please let me know now about this sort of surprising results, right, that we try to explain. How is it that if you are, and again, we do not know how many neurons the monkey is using to come to a decision. Well, we had expected, one could have expected that the more neurons you use, the better you get, and that your pooled signal here, so the better you get it, meaning here that your, that the signal to noise ratio would become better, and we see that it's enough that you have minimal correlation between the firing rate of one neuron and another neuron from one trial to another to explain the fact that, okay, you do not gain much by increasing the pool of neurons that you're using, okay? And as you remember, the individual neuron was almost as good as the average individual neuron was almost as good as the monkey, okay? Now, if you were to use 10,000 neurons, you would get maybe 2 or 3 times better than the monkey, but not 1,000,000 times better than the monkey. So we solved most of the problem by understanding this idea that partial correlation, it's called noise correlation between the neurons, can explain behavior to a great extent. Why do we call this noise correlation? Let me make this clear. Because we're talking about here trial-to-trial variation in the firing of one cell, yes, or another cell, and the covariation between them. So it's the trial-to-trial variation. Nothing's changed in the stimulus. So one calls this noise correlation. Okay, so that was the point I was trying to make. And then I want to sort of discuss another thing related to this, and that is, again, seminal studies done by Bill Newsom's group addressing the issue of, till now, we were talking about correlation. Okay, we were recording the neuron sensitivity, we were recording the monkey sensitivity, saying, well, they look quite the same. And we think, given that, 80 to 90% of the neurons in MT are sensitive to motion, is that it's most likely that the monkey uses these population of cells in MT to come to a decision. But we don't know anything about this. Well, how can we start studying this? Well, the idea is, and this is something that has developed dramatically in the last 10 years using optogenetics, but sort of the logic has remained sort of stems from these studies, and that's why I thought it's worthwhile mentioning them. And that is, okay, let's now, instead of recording the neurons, let's stimulate the neurons and see what is the effect on behavior. Okay, great. Now, what are the prerequisites for doing such an experiment so that it would have a chance of success? So let me get this again, repeat this. Okay, we find a direction selective neuron. It has certain tuning. It prefers the upward motion versus the downward motion. Now, let's stimulate the neuron while the monkey sees the stimuli so that we will now basically bias the monkey's decision towards the preferred direction of the neuron, right? No, I would say wrong. Why wrong? One neuron is not going to do the job for you because, as we said, okay, often we kill the neuron as the electrode moves, and that doesn't have an impact on the monkey's decision. So clearly, one neuron is not enough, and I would say not even 10 neurons or 100, but you need a grand population of neurons. So in order, okay, so now you want to stimulate, I don't know, 1 million neurons, okay? Let's just get an idea. In a 1 cubic millimeter of cortex, typically there's between 50,000 and 100,000 neurons, okay? So you want to use a stimulating current so that you activate, I don't know, hundreds of thousands of neurons or something of that sort, okay? Now, again, for that requires another prerequisite, right? Because if you're going to stimulate through the electrode, you want to stimulate neurons which are similar to one another. Because if one has the preferred direction in that direction, the other one has in that direction, you're not going to get much, okay? So a prerequisite for doing something here and this is with electrical stimulation, we'll say something about that, is that the neurons are going to have similar properties. Nearby neurons are going to have similar properties. Okay, so as you know from, I hope you know, in primary visual cortex, these, I mentioned this very briefly, that there's these orientation selective columns, right, that nearby neurons have the same preferred orientation. Well, if you go to MT, you see that nearby neurons have similar preferred motion direction. So here's the electrode that has been moving from layer 1 to layer 6, almost in a perpendicular to cortex here. And you see here, so that's the track distance starting from 0 when you enter gray matter. And here is the preferred direction of the neurons. And how can you say that what's your sort of decision looking at this? Look at the preferred direction of neurons here, nearby neurons. It's pretty much the same, right? So you can think about this, that there's these columns here. Okay, so let me just illustrate this figuratively, exactly as you see here. Here's cortex from layer 1 to layer 6, and you move your electrode, you record the preferred directions of individual neurons here. So here's the first one, here's the second one, here's the third one, here's the fourth one, and they're pretty much the same. So, and at some point it changes, okay, and then you get, I don't know, something like that, right? So if you move here along the track distance here and the preferred direction hasn't changed much, it means that you have sort of a columnar organization. So you can think about all these neurons having a similar preferred direction. Now it's not quite, you see that there's a drop here, and the reason for this is that your movement of the electrode was not quite perpendicular to the cortex, but somewhat in an angle. Okay, so you expect this.
You move perpendicular.
Ideally, perpendicular, it should be a line here, right? All dots should be in a given preferred direction.
Why? That layer 1, the cortex is one direction?
No. So I'm saying they'd be all, ideally, they would have all dots would be at the same, have the same preferred direction.
From all layers?
Yes. And that is, okay, there is strong evidence that indeed there is this organization in columnar organization. So that's great because now we can move the electrode, okay, find an area which is relatively homogeneous in terms of the preferred direction of the neurons, and now place the electrode at the center of that, and now pass current to the electrode so that we activate you can think about this, a volume of neurons near the electrode that have the same preferred direction. And then we may expect to find that we are able to bias the monkey's decision when we are stimulating through the electrode.
Could you explain what's the bar of the y-axis?
So the y-axis is the direction of movement, the preferred direction of movement of each cell. Okay? So if it were, let me just make it clear, if the cells had the preferred direction of motion of each cell was independent of its position, okay, then the dots here should be, the one dot would be here, the next one next to it could have a preferred direction of, 240, and there should be a great spread of the dots here. The fact that if you move here, you see that nearby dots that are separated, by 50 microns have the same preferred direction and suggests that there is a columnar organization. Okay, that was the point I was trying to make. And you can take advantage of it now. If you place your electrode here, you activate neurons that have similar preferred directions. So that's what you want to do, because there's no sense in activating neurons if each one has a different preferred direction, then you're just going to introduce noise to the system. But if all of them have the same preferred direction, you may have a chance of biasing the monkey's decision by stimulating them. And that's what Bill Newsom and Tony Mopshin have done. Okay, so these are original experiments from really 1990 or something like that. So the idea is very similar to what I described before, but you now find the receptive field of the neurons, place and find the preferred direction of these neurons. It's not one neuron, it's many neurons. Another thing that's important here is that receptor fields of the neurons are generally largely overlapping. Not completely overlapping, but largely overlapping. Again, if the receptor fields, if one neuron had a receptor field here and the other there, wouldn't make much sense to do the experiment. But since they overlap, you can place the stimulus at sort of the average receptor field position and the average preferred direction. And now, it's the same as we described before. The only thing that you do is that when you present the visual stimulus, you also stimulate through the electrode. So you have the electrode is placed here, and you stimulate through the electrode. And what you do is you stimulate, you use sort of a bipolar stimulus like that, okay? And you give it, there's a given amplitude of the stimulus, and there's a given frequency depending on this time between one pulse and another pulse. Okay? So you can basically vary either amplitude or frequency, and typically, in a minute, you use a frequency of, I don't know, 100 hertz or something like that. It doesn't really matter here. Okay? And the amplitudes of the order of 10 microamps or something like that. Yes?
Can you go back one slide for a second?
Backwards rather than forward. Okay. Yes.
You see that there's sort of a...
This one here?
Yes, over there, and also...
And this one here?
When you see the penetration of the electrode in the layers...
Yes.
And you see the graph above, you see that there's an overlap sort of degrees. You could be starting in layer... if we think that it's a column and you're not going perpendicular, so you'd have another group of neurons that are also sensitive to a certain degree. So you hitting a certain spot might not exactly...
Okay, so, okay, great point. Okay, so in this technique, there's no optical imaging. You don't know, you have no access to the cells, direct access to the cells. So all you know is you're moving your electrode in one direction, and you're assessing the preferred direction of the neurons in that direction, okay, along this track here. You have no idea what's happening in this dimension or in that dimension, right? Okay, so it's true, and we may actually mention this, that you do not always, you expect that sometimes you'll miss. I mean, you may be here having neurons that have one preferred direction, but if you were to look in this direction or in that direction, meaning closer to you or further to you, remember the cortex is a three-dimensional plane here, maybe just next to it you have neurons which have the opposite preferred direction, right? So you're somewhat you're guessing. You have no other, you're guessing, and your guess is based on the limited information that you have, and to some extent sometimes your guess may not be very good. And we'll see something about this that may explain this. But let me just get to the basics. The basics is what we said here is now that you're presenting the visual stimulus, and together with the visual stimulus, you're stimulating the neurons through the electrode. Okay, so these neurons, let's say, now these neurons have, this would be their preferred direction, right, if you're stimulating here, and this would be the null direction, okay, and so you're presenting a visual stimulus, and you're stimulating electrically through the electrode at the same time, and what do you expect? What do you expect? I didn't hear it. There was an answer?
Some bias in the decision.
Some bias in the decision. In what way? In
your stimulus way. The way of the neuron is stimulating.
Exactly. Not in the stimulus, in the preferred direction of the neurons that you stimulate. That's the point. That is exactly that. So, okay. And so here's just let's look at it. Here's just, one such experiment. So the x-axis here is the correlation of the dots. So positive here, let's look at this one just so it's easier to see. Positive means that the stimulus is in the preferred direction of the neurons, and in that case it would be leftward. And negative would mean that the stimulus is in the null direction. Okay? Now what you see here is the response without electrical stimulation. And what you see here is the response with electrical stimulation. Okay? I didn't explain what the y-axis is, so let's follow this and understand the logic here. Okay? So it's slightly different than the psychometric curve I've showed you before. The y-axis here is proportion preferred direction. Okay? So you have the neurons, they have a preferred direction. I said here leftward. Okay? And we're asking how many times did the monkey respond that the motion was in the preferred direction. Remember, the monkey has to say is it preferred or null on each trial, right? Now you're stimulating in some trials through the electrodes. In other trials, you do not stimulate through the electrode. And as I said, here the axis here is zero correlation, means it's completely random motion. Positive means that the motion is in the in the preferred direction. Negative is motion in the null direction. Okay, so let's think about, leave the microstimulation. Let's think first of all about the cases, the psychometric curve without microstimulation. Okay, let's look at this one just to make that point. Okay, if the stimuli is strong in the preferred direction, what do you expect the monkey to say? That it's in the preferred. And if the stimuli is strong in the null direction, what do you expect the monkey to say? That it's in a null. So he never says it's preferred. Okay, so here this is not correct answers. It's preferred direction. Okay, so he would never say that it's preferred direction. He'd always say it's null. It's the right, and of course that's the right response. Okay.
How do you stimulate in a direction?
Because you know what the stimulus is. You use a stimuli of a given coherence, either in the preferred or the null direction. Okay, so there's a and you're asking.
No, I'm talking about the stimulation.
The electrical stimulation. Okay, so the electrical stimulation is of a given amplitude and a frequency fixed one. Okay, to exert an effect. Okay, and we'll talk about this. What do I mean by an effect in a minute? But just to preempt your question, an effect is that the psychometric curve is shifted to the left, and we'll explain this in a minute. Okay. Different experiments. Yeah, in all cases you see that the psychometric curve is shifted to the left. Let's understand first of all. Okay, what would be perfect performance? Forget about the microstimulation. Perfect performance. What should it be like? If it's in the null direction, you should say no. Okay, should it be zero? And it's a preferred direction, you should say yes. Okay, so it should be a step function jumping in the positive values here to 1, negative values here to be at 0, right? Okay. So basically, if you look at the behavior, it's corrupted by noise, but it does seem to be something like that. Okay. Now let's think of the microstimulation. The microstimulation now adds a signal, and now the signal is what? That the person, you would expect that the person would be that the dots now seem to be moving in the preferred direction because you're stimulating beyond what's stimulated directly through the visual stimulus, a pool of neurons which basically encode the preferred direction, right? So think about this. Let's just think about, look at one example here, okay? For the 0% coherence, you see, okay, the complete random motion, and you see a major jump. So that now the monkey says in, 70% of the cases that the dots have moved in the preferred direction in the stimulated trials, while in the non-stimulated, 20% of the trials, okay? So notice, there's no stimulus on the screen. It's just random motion, okay? There's no net motion on the screen. But the microstimulation has a major effect, shifting this function leftward. And as I said, the easiest way to understand this is there's no information whatsoever, that there's this shift towards the preferred direction. Okay, and you see this in the vast majority of experiments. I won't get into the details here, okay, but just to show you here, you can measure the equivalent visual stimulus. That is the degree of shift here to the left. Okay, so any shift to the left would be, and you can measure this in terms of equivalent visual stimulus. Meaning, just to give you an intuition for this, okay, now you're stimulating the neurons, and they have a preferred direction. What sort of stimulus should you use so that it would look as if there's no net motion to the animal? Okay, so you should use now, of course, stimuli in a null direction, and the stronger stimulus you need to use in the null direction, that means that you have a stronger effect of the microstimulation. So that's the equivalent visual stimulus that we are talking about here. And you can see that in most cases it's here positive, meaning that you got an effect in the direction that you wanted, and the light bars here are the ones where it's statistically significant. Doesn't really matter, but it says, there's like, 200 experiments here, and there's just 3 in which it was in the wrong direction. Okay, so it's a very strong prediction here. You're stimulating the neurons, and you're affecting the monkey's behavior in a predictive direction. Okay, so that is the point here.
Here you excitement of the neurons.
Yeah, okay. Excellent point. Okay, so with microstimulation, it's a very I wouldn't say a brute force, but it's something where you're just exciting neurons next to the electrode. Are they excitatory, inhibitory? You have no control over this. Generally, in cortex, there's like 80% excitatory and 20% inhibitory, so you're affecting both. Okay, that's the beauty of the new techniques, that you can now target this and now stimulate specific pyramidal cells in a given layer and so on and so forth. With the optogenetics that you are unable to do here. But the interesting thing, even with such a crude measure, you could get a clear effect. Okay. Now, a few points to what I mentioned before in terms of where do you place the electrode. Remember, you can move the electrode in one direction here, and you try to find the optimal position so that the neurons next to it have a similar preferred direction. Okay, and you can see that the position of the electrode could be very, very dramatic, could have dramatic effect. So this is the equivalent visual stimulus, the effective microstimulation, 0 meaning no effect. Okay, and you see that when you're moving from one depth, 100 microns, no more than 100 microns, you get a major effect here, hardly any effect here, and hardly any effect here. Okay, and why is that? Part of it is because you want to stimulate homogeneous groups of neurons. Okay, and if you're missing, and once you get to this heterogeneity, okay, if you're missing the sweet spot where you're targeting a homogeneous group of neurons, you don't get much of an effect. So here's one such experiment. Here's another such experiment showing the importance of where the electrode is. And of course, the reason also is that we don't know what happens in the other dimension. So as remember, we have some information about how the neurons are in this dimension, but we have no idea about what they are, the preferences in the other dimensions. So that's another reason why we may miss sometimes. Okay, another important point here is that, okay, what is the effect that we're exerting? How do we understand this? Okay, so there's 2 ways to think about it. Okay, you're stimulating the neurons. Are you generating a percept of something like a motion after effect? Okay, so that you're generating a percept of more dots moving in that direction. Well, a few interesting ways to think about it. So one way is that you have a perceptual effect. The other is that, okay, think about it. You can think that you're actually affecting decision processes directly, not perception, but decision processes. What do I mean by that? Let's say that you see the motion, and the motion for you is downward. But now you're stimulating these cells, and these cells is like a bird telling you, okay, it's upward, and you can't ignore it, okay? So you say upward, and you're affecting decision, okay? Well, if that were the case, if it were the decision process, it's hard to differentiate between the two. But one thing you can look at is if there's any specificity, spatial specificity, okay? So the way you can test this is now place the stimulus either, here's the fixation point. Once you place the visual stimulus at the receptor field of the neurons that you're going to stimulate, and once you place it in a remote aperture. Meaning now, so what do I mean by here? A remote aperture means, okay, I'm stimulating the cells. Okay, these cells are sensitive to motion in that position in space. Okay, but now my stimulus is presented here. What do you expect now? I'm stimulating these cells, but the monkey has to make decisions about movement going up or down here. Okay? What do you expect in that case? Would it make a difference? It wouldn't make a difference if it's like the bird telling you it's upward, upward. It doesn't really matter where is it in the world. But you can think, I would think that it would make a big difference in the sense that, you know, if you are the monkey, okay, and you have to tell motion which is happening here. The fact that you have stimulation here, okay, another electrical activity in this place, that's irrelevant. Ignore that. That's not very relevant for you because you have to sort of place your attention, make decisions about here. I'm focusing on you, and I have to tell motion here that the fact that, you know, someone raised his hand there is irrelevant for me to tell if you raise your hand up or brought it down. Okay, and indeed, if we look here, if the stimulus is placed in the receptive field, you'll get a great microstimulation effect. That's the microstimulation effect drawn here. Okay, so you see a major effect in terms of the microstimulation. But if the stimulus is placed in a remote aperture, okay, then the cell's firing has no effect. Okay, so microstimulating them has no effect, and you can see here that the two distributions are overlapping. Okay, no effect here, great effect here. This is when the stimulus is placed in the receptive field. This is when it's placed in a remote aperture. So there's spatial specificity. That's the point I was trying to make. Okay, the effects of microstimulation are spatially localized.
Why is decision spatially independent?
Spatially local. As I said, because I think that you are, if you have to make, just putting you in the spot of the monkey, if you have to make a decision about motion here, motion elsewhere in the world, in a very different position, it's irrelevant for you because I'm focusing on you. Okay? I don't care about motion in the other. And you'd think that the monkey is also being able to tell this. He has to tell the motion of the tiger in one position, the fact that the leaves in other positions are now shaking, that's irrelevant for him. Okay? So it's the same idea. Of course, that's what. I mean, that was the whole point. That was the whole point. Okay. First of all, the effect of a microstimulation. Okay, just to wrap things up, the idea here was to introduce causality. As we were talking before, we were talking about a correlation. You know, you're seeing that the neurons are as sensitive as the monkey, and so on and so forth. But the element of causality was missing. Here, you're stimulating the neurons, and you're generating a perceptual decision, which is the prediction, according to the prediction. So that's the point I was trying to stress. Okay, just to finish here. Okay, what would happen if you now increase the frequency, right? So instead of using sort of in a given amplitude, you're using instead of giving the stimuli every 10 milliseconds, as in the case of 100 hertz, you give this every 2 milliseconds as the case of 500 hertz. What do you expect?
Higher firing?
Yes, of course. So you're generating higher firing rates of the neurons. At some point that would saturate because they have a limited capability of firing. But within a reasonable dynamic range, the more you increase the frequency of electrical stimulation, the greater firing these cells you produce in these cells, and therefore you should get a greater effect. Indeed, that is the case here. So look here, two such experiments in which you increase the current frequency from 0 hertz to 500 hertz, and you see that the psychometric curves shift gradually leftward, meaning that you get a greater and greater effect. Okay, as you increase the firing, as you increase the frequency from 25 hertz to 500 hertz. That's an average across, I don't know, many such experiments. So that's one experiment, that's another experiment. You see that that's indeed the case. Now, what about if you were to increase the amplitude? So instead of increasing here the frequency, you'd use a stronger stimulus. Okay. Any predictions here? So remember, you're placing your electrode here, and you're trying to sort of, as you increase the amplitude, let me give you another clue here, you're affecting a larger and larger volume of neurons.
More noise.
Okay, so no, not initially. I mean, so what you want to do initially when you're increasing the amplitude, you're sort of recruiting into the game more and more neurons that have a similar preferred direction. So initially you're going to get more signal, but at some point you're starting to cross and now activate neurons that have different directionalities, and even opposite directionalities, and of course then you're going to get noise. And that indeed is what you see here. So you see, again, if you start from, I don't know, 5 microamps and increase it to 80 microamps, initially this thing shifts to the left and maintains the same slope, meaning it maintains the same sensitivity, but as you're increasing the current amplitude beyond some level, you get to here. So the monkey is completely confused, okay? So you're introducing noise and you're confusing the monkey's decision. So indeed, there's, as you increase the amplitude, you're initially gaining signal, and then you're introducing noise to the system. Okay, I don't think I have time, but I'll mention this just in a few words. I mean, this is an interesting question, and that is, okay, can you have perceptual learning? If we are to do, let me just explain. If we are to do this experiment over and over again, we as humans, and apparently also monkeys, they improve with time, okay? So they get better, and you can see it here. I mean, that's just to show you, in the case, okay, so you present the motion here, and you look at, here's the motion strength from 0% coherence to 100% coherence, and this is time here, and maybe this is better to show this. You can compute what is the threshold in the early sessions and the threshold at the late sessions, and you see that basically this is going down, meaning that the threshold gets better. And this is also a function of time. So the more time you have, the more time you have to integrate the information. Okay, so if the stimulus is presented for half a second, you're not as good as you are than when it's presented for 1 second, because you can integrate the information across time. Okay, but the point here is that you get improvement, and the question is, okay, what can cause an improvement? And since we don't have much time, I won't go over all the details, just to say that we were talking about this summation here, right? So how can we understand this, okay? So evidence number 1, yes, the monkey improves with time. Okay, how can we understand it? Okay, so one way to understand this is that cells in MT get better, right? That those motion detectors that you have, now they're becoming more sensitive with time, okay? More sensitive with practice, I mean. That's not the case. So how else can we understand this? If it's not happening in that level, there's cells in a higher order area called LIP, which are extracting the information from those cells in MT. And basically, just to sort of focus on this, what you can see is the following. So here's time here, okay? You start from 0 is the time at which the stimulus is shown, and you see the cell's response in LIP now for a stimulus presented in the preferred direction and in the null direction. So what you can see here is that there's an increase in the firing rate in the preferred direction, a drop in the firing rate in the null direction, okay? And the higher the coherence, the faster the increase here. Why? Because you think about these cells in LIP as the integrators of information, okay? So remember I talked about an integrator? So here's this integrator of information. It's getting information from all these empty cells here, okay? And it's summing up this information. So if the coherence is stronger, what do you expect? It's easier, right? You get to a decision about what is the direction of motion. Is it preferred or no? Faster, right? Because it's an easier trial. Now look here. Here we show the response of that cell during a saccade. Okay, so these cells are not just sensitive to the sensory stimulus; they're also motion sensitive. So if the motion is done in one direction, okay, so here's a saccade being made to the preferred direction, you get a strong response. If a saccade is being made to the opposite direction, this way, there's much less of a response. Okay. Okay, so this difference has to be is saccade related. 0 is the time at which the saccade begins, And notice that there's this increase before the saccade actually is originating. Why? Because these cells are related to the decision. What am I going to do? Am I going to do a saccade in one direction, in the preferred direction, or a saccade in the opposite direction? Okay? Okay, so, and as you see here, the stronger the stimulus, the faster they go up. Okay, so if you're looking at a very weak signal, the slope here is slower. But another thing to notice here is look at the 0% coherent stimuli. That's where I'm going to end. Okay? Look at this one and that one. Okay? Although there's no net stimulus, no motion in the stimulus, this cell is firing much stronger when the monkey is going to decide, I'm going to make a saccade in the preferred direction than if I'm going to make a saccade in another direction. So that, again, we've seen something like that. But it's much stronger here. It's pointing out to what the monkey's decision is going to be. Is it going to be a saccade in the preferred direction, or is it going to be a saccade in another direction? Now, this is sort of something that I may take your time next time a little just to finish this point, and that is that we've seen learning, right? The monkey's improving. I said that the learning does not occur because the neurons in MT become more sensitive. How can we understand this? Well, we can understand this in terms of the pooling of the signals of these MT neurons in these sort of integrated into these integrated cells. And indeed, if you look here, you see in the early sessions versus the last sessions, look at this. So again, this is time from the start of the stimulus. And this is sort of the integration process that takes place in these cells. Okay, so there's a number of cells here, but you can see that it's always sort of an increase of the firing rate if it's in the preferred direction, a decrease of the firing rate if it's in another direction. And it's somewhat irrespective of the coherence level. But look at what happens in the late sessions when the monkey has become better. What can you see? You can see here that compare this to this one. Slope is much faster. You come to a decision much faster, right? So you become more effective in your decisions in the late sessions than compared to the early sessions. This is an average, okay? It's not the same cells. Unfortunately, it's not the same cell, but this is an average. It's showing that you're now sort of pooling information in a more effective way. And I'll stop here because I ran out of time. And next time we have the students presenting, I will start with giving sort of 10 minutes sort of intro to the issue because we were talking about motion. We're going to talk about object recognition in the next session, but we'll try to tie it up together.